Okay, this is Chemistry Chapter 13, Lecture 2. We're starting on page 3 of your notes up at the top, and you'll want to have your Chapter 13 table sheet ready to go. And our first, the on your own problem I'm going to work first is on page 433. All right, just going through your notes here, starting at the top, determining delta H by Hess's law. So using Hess's law to determine delta H is more accurate than bond energy method. Because it takes phase into account. So the phase, solid, liquid, gas, aqueous, okay? And you can read through the notes all you want. You need to read through the book about a state function. That'll help you answer one of the review questions. And a couple of things on the notes that are key is that the enthalpy of any element in its elemental form, so that's its normal elemental form, so like H2, O2, if it's a homonuclear diatomic, hydrogen's normally a gas, oxygen's normally a gas. So as long as it's in its form where it is, where it's normally is at standard conditions, okay, so room temperature and pressure, then the enthalpy is defined as 0, okay, and standard conditions 25 degrees Celsius and 1 atmosphere of pressure. So Hess's law equation okay, the equation that you're going to have to memorize, that's delta H, and the little degree symbol just means standard conditions, again 25 Celsius, 1 atmosphere of pressure, is equal to the sum, that Greek sigma means to sum up, of the enthalpy of formation of the products minus the sum of the enthalpy of formation at standard conditions of the reactants. Now that equation looks awful, but it's really not. It's really not. I'm going to leave it up there while we work problem 13.4. Again, have your table ready, and we're going to use table 13.2. All right, so on your own 13.4 says that when you use a pocket cigarette lighter, you're burning gaseous butane. Assume it's complete combustion. What's delta H? And we want to use the bond. We want to use Hess's law, not bond energy, okay? Because we should know all of the phases. So gaseous butane would be C4H10. It's complete combustion, so plus O2 gas. It's going to make CO2 gas plus H2O gas. Now we need to get our coefficients. We have to balance it. If you go through the balancing process, of course we probably put a 4 right here. Now don't write this down yet because I'm going to be doing some erasing, but a 4 because we have 4 carbons, 10 hydrogens, so let's put a 5. Then that would give us 8 plus 5, 13 oxygens, so we need 13 halves. And then we need to multiply everything through by 2. So that's going to give us a 2, 13, I'm going to mark that out, 8, and 10. Right, you do have to have it balanced correctly. So we'll go straight into getting delta H using table 2. And this time it's products minus reactants. So we have our first product, CO2, we have 8 moles of that. I don't need the Lewis structure, just need to go straight to the table. So for this first one, we'll look at the table. Where is CO2 gas? Well, it's right here. And delta H of formation, enthalpy of formation, is negative 394 kilojoules per mole. We want to add the other product, 10 moles of water gas. That's the very first one in the table, negative 242. Now we're going to subtract out the reactant. So minus 2 moles. Our first reactant, C4H10. All right, looking at that in your table, it's at the very last column, the third one down, negative 126. And then you'll see O2 is not in the table. That's because the enthalpy of an element in its natural state, a single element in its natural state, is 0. So that's just for oxygen minus 0. All right, so you can work along in your calculator, but that's going to be negative 3152 for 8 times negative 394 plus negative 2420. That's 10 times negative 242. And then minus minus makes a plus, and that will be 252. So that is negative 5,320 kilojoules. Makes sense that it's negative. This is a combustion reaction, should release heat to the atmosphere. Okay, so really easier than the bond energy method. You don't have to fool with the Lewis structures. You just got to get a balanced chemical equation and make sure you do product minus reactant and not the other way around. So I think I can fit 13.5 on here because I don't have to balance the equation. It says, reading through the problem, read along with me. We're on page 433. All right. When you, in order to make shells that house and protect them, many shellfish take solid lime from the ocean floor, react it with gaseous carbon dioxide. So CaO, solid lime, plus gaseous carbon dioxide, and that makes calcium carbonate, a major component of their shell. And of course the shell is going to be solid. Calcium carbonate, CaCO3. All right, so you might have to remember back to your chapter 9, but this carbonate has a -2 charge, calcium +2, so after the big switcheroo, it would just be CaCO3, and it's solid, and that is balanced. Okay, you count them up, but it's balanced. So we want to know what's the delta H, okay? We're going to use the table. We have 1 mole. Again, we got to start with the products. That's the most common mistake. Accidentally do reactants minus products. It's products minus the reactants. So 1 mole. And let's look in table 2. Find CaCO3 solid. All right, there it is, negative 1207. Now we're going to subtract out the 2 reactants. -1 mole. CaO solid. That's at the bottom of the second column of numbers. All right, and that is negative 635. And then subtract out 1 mole of CO2 gas. All right, CO2 gas is negative 394. Make sure you're using the right table. So that will be negative 1207 plus 635, minus minus makes a plus, and then another minus minus, plus 394. So that'll be negative 178 kilojoules. Remember the moles and the moles cancel, leaving kilojoules. So that is exothermic. So when a shellfish makes their shell, they release a little bit of heat to the ocean. Okay, so I'm going to, let's go on to page 4 in your notes. And I'm going to erase, so if you're still writing, go ahead and pause your video. Now we're going to continue on with Hess's law, but we're going to use stoichiometry. All right, and we're going to work 2 more problems at the bottom of page 435. So no vocab to go through here. So we've got 13.6, page 435. And I'll show you how that you can use stoichiometry when determining delta H. So it says ethane gas has also been considered a fuel for automobiles because, like octane, it releases a lot of energy when it's burned. How many kilojoules of energy are released when 250 grams of ethane undergo complete combustion? Okay, so we do have to get a chemical equation, C2H6, and it's gas. All right, complete combustion would be oxygen gas. And that makes, you know this, you've done it so many times, CO2 plus H2O. Right, we do have to balance. All right, so I've got 2 carbons here. I'm going to try a 2 there. 6 hydrogens here, so let's put a 3 here. Let's add them up. We have 7 oxygens on this side, so I need a 7/2. So I need to multiply everything through by 2. So I'd have a 2, a 7, 4, and a 6 for those coefficients. So we need to get delta H, and then we can see how much energy is released after we get delta H. So delta H, remember, using Hess's law, we're going to sum up the enthalpy of formation of the products minus the sum of the enthalpy of formations of the reactants. Okay, so that will be our first product, 4 moles of CO2. So 4 moles. Look up CO2 in table 2. CO2 gas, that's negative 394. We're going to add to that our other product, 6 moles of water gas. If you look that up, it's negative 242. And then subtract out our first reactant, 2 moles of C2H6 gas. All right, C2H6 gas is negative 84.7. It's in that 3rd column. And then oxygen is just 0, so minus 0 for oxygen. All right, get your calculator out. Let's multiply all this out. We've got negative 15, 4 times negative 394, negative 1576. 6 times negative 242, negative 1452. Plus, minus minus makes a plus, 2 times 84.7, so that's 169.4. That's negative 2858.6 kilojoules. Okay, now we can do the stoichiometry. It says how many kilojoules are released when 250 grams of ethane are burned. Okay, so you start with the mass of ethane, 250 grams of C2H6. Let's put that over 1. We need to change that to moles of ethane. Okay, so we've got 1 mole. What's the molecular mass of C2H6? Well, it's going to be 12 times 2, 24 plus 6, so 30 grams. And here's where the energy comes in. So we have It's not negative, all right? We're just releasing energy. The negative tells you it's exothermic. It goes in as a product, but 2,858.6 kilojoules. Okay, so we just, again, it's not negative. And what goes in the denominator? Well, we need to get rid of moles of C2H6. That 2858.6 kilojoules is per 2 moles of C2H6. You must use the stoichiometric coefficient. So 2 moles of C2H6. And that is 11,910.8 kilojoules. Pretty good. A lot of energy released. Okay, I'm going to work the other enthalpy and stoichiometry problem. If you need to pause the video, you're still writing. All right, 13.7 says, when mined, coal has a small amount of sulfur in it. When that coal is burned in a power plant, the sulfur burns right along with it, producing SO3 gas. When the SO3 gas reacts with water in the air, it produces sulfuric acid according to the following equation. So we have H2O plus sulfur trioxide, and that makes sulfuric acid. Battery acid. So that's acid rain, not a happy thing. Sulfuric acid produced in this manner falls to earth as acid rain. How much energy is produced when 50 grams of H2SO4 are produced in this way? All right, we need to get the delta H for this reaction, and then we can use the 50 grams to get the amount of energy produced by 50 grams. Okay, so delta H, and it's nice, we didn't have to write out the reaction and balance it. The author gave us the reaction. So delta H, all right, it's going to be the product, okay, so 1 mole of H2SO4. Okay, if you'll look that up in table 2, you'll see that that is negative 814 kilojoules per mole. Minus 1 mole of H2O gas, and then we have to subtract out the other reactant, 1 mole of SO3 gas, which is negative 396. Okay, so that'd be negative 814. Negative negative makes a plus 242 plus 396. So that's negative 176 kilojoules. Now we can use the stoichiometric process. So we have 50 grams of H2SO4. We need to convert that to moles, so 1 mole. If you add up H2SO4, you'll get 98.1 grams per mole. And now we're going to do this stoichiometry part. 176 kilojoules are released. Again, don't make it negative. Per, look at the stoichiometric coefficient for H2SO4, it's just 1. So 1 mole of H2SO4. And that is 89.7 kilojoules, so not nearly as much energy released per mole as the last problem. That does it for lecture 2. We're all the way through page 4 in your notes. We'll start on page 5 for the next lecture, and happy chemistry.